Welcome to the wonderful world of physics. This is Physics 102A, Chapter 3 homework. Starting with number 17, it says the position vector, negative 2.3 meters I hat minus 4.0 meters j hat, makes a direction angle of what? Let's draw the picture. So negative 2.3 and negative 4.0, as we draw the picture, we draw negative 2.3, so 2.3 to the left, 4.0 down. And we see it's a third quadrant angle. So to find the angle, we take the arctan of y over x, the arctan of negative 4 over negative 2.3. And when we do that in the calculator, it gives 60 degrees. However, then we have to recognize that when we take the arctan, it will give us a first quadrant answer. We need to adjust for the fact that we're in the third quadrant. So 60 degrees, which is in the direction that my marker is pointing, that's 60 degrees. We're exactly 180 degrees off, so to put in the third quadrant, we add 60 plus 180 and get 240 degrees. Number 19, your car's instantaneous velocity is 11.9 I hat plus 19.5 j hat meters per second. Your speed is what? So it's asking for the magnitude of the vector. Here I've written out the vector, and then the magnitude is, we're going to use Pythagorean theorem, square root of the x component squared plus the y component squared. And we get 22.8 meters per second. Now I've also drawn the picture, and as you can see, it makes a right triangle, and we're looking for the length of that hypotenuse. So 22.8 meters per second. Number 21, the maximum range on level ground of a projectile launched at 25.5 meters per second is, well, here's the range equation, v naught squared times sine 2 theta over g. Maximum range will occur at a 45 degree angle. So I've plugged in 2 times 45 degrees, that makes 90 degrees. Sine of 90 is 1. So at maximum range, it becomes v naught squared over g. We plug in the values, g being 9.8 meters per second squared, and we get 66.4 meters as the maximum range. Number 27, what are all the angles in a right triangle with sides 3, 4, and 5 meters? So some simple trigonometry. I've drawn a picture here. I've called the angles alpha, beta, and gamma. It's already telling us that it's a right triangle. And so we have 3, 4, 5. The hypotenuse is the longest one. The right angle is opposite that hypotenuse. So we know gamma is 90 degrees. Now, just for fun, I use the law of cosines to prove that that first angle is actually, that gamma is actually 90 degrees. And you can actually ignore and skip this step. We're recognizing it is a right triangle because it says that. And so the angle opposite the longest side will be 90 degrees. However, here's proof of it. But to find the other angles, let's find angle alpha. Now you look at the triangle and you see that alpha, its adjacent side is 3, its opposite side is 4, and its hypotenuse is 5. So we're going to use one of the 3 trigonometric functions, either sine, cosine, or tangent, to figure out what it is. I've chosen cosine. So cosine of alpha is the adjacent side over the hypotenuse, 3 over 5, which means alpha is the arc cosine of 3/5, which is 53.1 degrees. To find beta, we recognize that its adjacent side is 4, its opposite side is 3, the hypotenuse is 5, and we can use either sine, cosine, or tangent. I've chosen to use cosine. So cosine of beta is adjacent over hypotenuse 4/5. So we're going to do beta is arc cosine of 4/5 equals 36.9 degrees. By the way, if you are plugging into your calculator arc cosine of 3/5 and you're not getting 53.1 degrees, or arc cosine of 4/5 and you're not getting 36.9 degrees, there's a chance that your calculator is in radians mode. So you need to turn it to degrees mode. Number 33. A sign on a mountain road reads, caution, 6-degree downgrade for next 5.5 kilometers. by how much will your elevation have changed after you complete that stretch of road? So the next 5.5 kilometers of road, there's a downgrade, and so we can draw the triangle like this. There's a 6-degree angle, and the hypotenuse is the road we're going to travel on, 5.5 kilometers, and it's asking how much is the elevation dropped. So setting up the trig function, the sine of 6 degrees is opposite over hypotenuse, so y over 5.5 kilometers, which means y is 5.5 kilometers times sine of 6 degrees, which is 0.575 kilometers or 575 meters. Number 37 gives two vectors, and you can see I've written those two vectors R1 and R2 up at the top of the page. And 37 asks us for the magnitude and direction of both of those vectors. So we'll start with R1. The magnitude of a vector is Pythagorean theorem. We're going to take the square root of the x component squared plus the y component squared. And in this case of R1, we get 5.61 meters. For its direction, the arctan is the y component over the x component. And we get negative 64.76 degrees. Now it's important that we draw a picture so that we can assess what quadrant this is in, and if in fact the answer we've been given is correct. So I've drawn R1, and here we have negative 64.76 degrees is what the calculator gave us, and yeah, that's 64.76 below the x-axis. So the calculator will give a quadrant 2 answer. However, normally we express angles in terms of a positive angle between 0 and 360. So while negative 64.76 degrees, or I can round that to negative 65, is correct, we're going to give that in the range between 0 and 360. So rather than thinking about how much it is clockwise from the x-axis, we want to know what it is counterclockwise in the positive direction from the x-axis. So all you do is just add 360, and we get 295 degrees. Now for R2, I've written the vector up above. You can see I've drawn the picture right here. It's a quadrant 2 answer. So for the magnitude, I've used Pythagorean theorem. R2 is the square root of x squared plus y squared, so 3.69 meters. Theta 2 is the arctan of the y component over the x component. And that gives me negative 15.4 degrees. But we look at the picture, negative 15.4 would be a shallow angle in the fourth quadrant. Our vector is in the second quadrant. So we recognize this is a case where our answer is 180 degrees off from what we're looking for. So all you do is take what the calculator gives you, negative 15.4 degrees, add 180, that puts it in the second quadrant, and I'll round that to the nearest degree and get 165 degrees. Number 41, find the angle between the two vectors. Hint, find the angle each makes with the x-axis. All right, so there's the two vectors from the previous example. And we know that R1 was negative 65 degrees. So you see in the picture, I've shown that it makes a 65-degree angle with the x-axis. We know that R2 makes a 165-degree angle. I'm just rounding to the nearest degree here. So this 65 plus this 165 is 230 degrees. Now, as the question is asking, find the angle between the two vectors. Yes, 230 degrees is correct, but we should probably give the smaller angle, because if we go around the other way, down under those angles, it'll give a smaller angle. And so let's do that. And for that, we can just do 360, the full circle, minus the 230 that we got up here, and get 130 degrees. Now, I've done that rounding to the nearest degree. More precisely, I should have taken the answers that we got for the previous problem were not 65, but 64.76 degrees, and then added 164.6 degrees to get 229.4. Subtracting away 360, I get 130.6 degrees. So the answer, rounded to the nearest degree, is 131 degrees, and that is more precise. So what this shows you is the first way I did it, rounding along the way, actually added a little bit of error into my final answer. So the correct answer really should be rounded to 131 degrees. For number 43, find the x and y components of these vectors in the xy plane. And so these are new vectors here. It says vector A has magnitude 6.4 meters, direction angle 80 degrees. B has magnitude 13 meters, direction 30 degrees. All right, and then we'll get to C. So with A, finding the x and y components, the x component is going to be A cosine alpha, and I've called the angle of it alpha. So A cosine alpha, so 6.4 meters times cosine 80 degrees, and we get 1.1 meters. The y component of A is A sine alpha, 6.4 meters times sine 80 degrees, and that gives 6.3 meters. You do the same for B. In each case, for a vector, the x component is the magnitude times the cosine of the angle. The y component is the magnitude times the sine of the angle. So you can see the answers that I've gotten here. With part C, or vector C, it says in the problem, C has a magnitude 10 meters and points in the negative y direction. So just reading that without doing any math, you know right away that its x component is 0 because it's pointing in the y direction. And the picture confirms that there is no x component. However, the math shows 10 meters times cosine 270 degrees is 0 meters. And then the y component, negative 10 meters. Number 51, a snail crawling on a sheet of graph paper goes from the origin to the point 5.6 centimeters and 4.3 centimeters in 1 minute. Find its average velocity and average speed. Well, average velocity is, you can see the formula up above, it's the displacement vector divided by the time. So displacement vector is final position minus initial position. So it ends up at 5.6 and 4.3 centimeters. It started at the origin 0, 0. So in the numerator, when we subtract that, we find the displacement vector. It's 5.6 and 4.3 centimeters. Divide by 60 seconds. So the average velocity is going to be these x and y components divided by 60 seconds. So you should get, in the x direction, 0.0933 I hat. In the y direction, 0.07167 j hat, centimeters per second. If we want to know the speed, that's the magnitude of the velocity, the average speed, we'll use Pythagorean theorem. So the x component squared plus the y component squared. And that gives us 0.1177 centimeters per second, or we can say 1.18 times 10 to the negative 3 meters per second. Number 55, in this problem, it says, let the positive x-axis be horizontal, positive y-axis be straight up. A rocket is launched from rest on the ground. After 55 seconds, its speed is 950 meters per second in a direction 75 degrees above the horizontal. Find the components of the rocket's velocity vector at that time and its average acceleration for the first 55 seconds of flight. There I've drawn the picture, 75-degree angle from the ground. Speed is 950 meters per second after 55 seconds. So at that moment, we can say that its x component of velocity is v cosine theta, and that becomes 245.9 meters per second. Y component is v sine theta, that becomes 917.6 meters per second. Now question B, find its average acceleration for the first 55 seconds of flight. Well, average acceleration is difference in velocity vector divided by time. So we have Vx, Vy minus 0, 0. so final minus initial, divide by 55 seconds. And that becomes, in the x direction, when you do all that calculation, 4.47 meters per second squared, and in the y direction, 16.68 meters per second squared. And here it is in I hat, j hat notation, 4.47 I hat plus 16.68 j hat meters per second squared. Number 57. A baseball traveling horizontally at 32 meters per second is struck by the bat, giving it a speed of 36 meters per second in the opposite direction. Find the change in the ball's velocity. If the ball was in contact with the bat for 0.75 milliseconds, what was its average acceleration? Give both magnitude and direction. The picture is important here because it's not just simply a matter of saying that it went from 32 to 36 meters per second, because that would be only a change of 4 meters per second. Rather, it went 32 meters per second in one direction, and then it got stopped, turned around, and 36 meters per second in the other direction. So it actually changed by 68 meters per second. We can mathematically show this by change in velocity vector is final minus initial. And if we make the initial be in the positive direction to the right, and the final be in the negative direction, then that becomes final minus initial is negative 36 minus 32, and that becomes negative 68 meters per second, meaning the total change in velocity is 68 meters per second to the left, as I've drawn it. So the magnitude of the change of velocity is 68 meters per second. Question B asks if the ball was in contact with the bat for 0.75 milliseconds, what was its average acceleration? So average acceleration is change in velocity divided by time. I'm just doing the magnitude of the change in velocity. 68 meters per second divided by, it says 0.75 milliseconds, so that's 0.75 times 10 to the negative third seconds, and we get 9.1 times 10 to the fourth meters per second squared. And it's clearly accelerated to the left, so we can say the direction is opposite the original trajectory. Number 63 is a problem with projectile motion. It says a baseball hit just above the ground leaves the bat at 27 meters per second at 45 degrees above the horizontal. How far away does the ball strike the ground? How much time is the ball in the air? What is its maximum height? All right, so I've drawn a picture. I've written the given information. V naught is 27 meters per second. Theta naught is 45 degrees. To answer how far it goes, this is actually a great setup for the range equation. If it's coming down to the same height that it started, just above the ground and at the ground, that's about the same, we can use the range equation to see how far does it go. So range equation is V naught squared times sine 2 theta naught over g. You can see I've plugged in the numbers. Sine of 2 times 45 degrees becomes sine of 90. And in the end, we get 74.4 meters. Question B asks, how much time is the ball in the air? Well, we can think of this as a one-dimensional vertical problem. So let's consider just the y components. And you can see my marker. We're going to think of it just in the y direction. It's going to go up and it's going to come down. And as long as we just deal with the y component of velocity, it's the same time as if we just threw a ball up straight up at that speed. So let's think about it that way. The y component of velocity initially is 27 meters per second times the sine of the angle, 45 degrees. So the y component of velocity is 19.092 meters per second. And we're going to treat it as if we just threw it straight up at that speed. Now, Vy equals V naught y plus acceleration in the y direction times t. And so when it comes back down to the ground, its y velocity is going to be the opposite of the original y velocity. If you throw it up at 19.092 meters per second, when it's back on the ground, it'll be going negative 19.02 or 19.092 meters per second. So I'm replacing v sub y with negative v naught y. So we have negative v naught y equals v naught y, and in place of acceleration in the y direction, I'm going to say plus negative g, because I've made up be the positive y direction, so acceleration is negative g. And now I can solve for t. It's 2 times v naught y over g, and we get 3.896 seconds. Now here I've written a little by the way comment. Now that we know the time in the air, we can actually go back and check our answer to part A, because in the horizontal direction, now we're treating it just horizontally. The distance it goes is v naught x times t. And now we know what t is. So we can say v naught, which is 27, times the cosine of the angle, which is 45 degrees. And now we're going to multiply it by the time, 3.896. And that gives 74.4 meters, and it confirms our answer to part A. Now, if in doing this check, we don't get 74.4 meters, then that tells us something has gone wrong, either with how we did part A or with how we did part B. But we can use that as a check between A and B. Now, part C says, what is its maximum height? How high does this go? So we're going to think about the vertical direction. And just in the vertical direction, vy squared equals v naught y squared plus 2 acceleration in the y direction times delta y. And we want to solve for delta y when it's at its maximum height. So here I've solved for delta y. And the first term in the numerator, vy squared, well, at its maximum height, the y component of its velocity is 0. So that goes away. We're left with minus v naught squared over negative 2g. Plug in those values, and we get 18.6 meters. Number 65. A ball rolls off a horizontal table at 0.30 meters per second and strikes the ground 0.15 meters horizontally from the base of the table. Here I've drawn a picture. It's rolling off, so the origin of its motion, of its projectile motion, is at 0, 0. I've drawn from there the x where it hits is 0.15. Because the motion is downward, I've chosen to make the positive y direction be down, and that means acceleration is going to be positive 9.80. And we're going to find out, or we don't know, how far it's fallen, how high the table is. And in fact, that's what question A is asking. We do know that its original velocity, up here at the top where my marker is, v naught, is all horizontal. That's the point of where it says it rolls off a horizontal table. So at the moment, right as it's leaving the table, it has no vertical velocity. It's all horizontal. So we can say v naught x is 0.30 meters per second. Well, to find how tall the table is, let's first use the horizontal component, the x component of motion, to figure out how much time it was in the air. Then once we know the time, we can focus on the vertical. How far did it drop? So to find t, evaluating just the horizontal motion, we can say x equals v naught x t. T, therefore, is x over v naught x. Well, we know x, it went a distance of 0.15 meters, divided by original x velocity is 0.30 meters per second. In fact, that's the all of the x velocity all the time, and that is 0.50 seconds. So it's falling for 0.50 seconds. Once we know that time, now we're going to examine the vertical component of velocity. And let's use this kinematic equation that involves time and initial velocity and position. So we get y equals y naught, which is 0. That's what I established in the picture, the origin at 0, plus v naught yt. Well, right as it rolled off the table, it had no velocity in the y direction, so that goes away, equals 1/2 acceleration times t squared. So we can treat it as if it just dropped straight down. So y equals half of g, which is 4.9 meters per second squared, times 0.5 seconds squared, and we get a drop of 1.225 meters. Now, question B gives us a different scenario. It says, if another ball rolls off the same table at 0.6 meters per second, how far from the base of the table does it hit? Okay, so same table drop, it's still going to drop 1.225 meters. And if it's dropping the same distance, it's still going to fall in the same amount of time, no matter how fast it's going horizontally. Whether it drops straight down or it's going slowly horizontally or fast horizontally, it's going to drop the same distance in the same time. So its time is going to be 0.50 seconds, no matter how fast it's rolling. So now we can say its horizontal distance is v naught x times t, 0.6 meters per second times the time of 0.5 seconds that it's in the air, and we get 0.30 meters, which is twice as far as the first ball. So if it's rolling twice as fast, it's going to go twice as far horizontally. Number 71. Guns on World War II battleships could shell targets 15 kilometers away. Find the minimum launch speed needed to achieve that range, and B, the shell's flight time under these conditions. Okay? Minimum speed to achieve that means for the given speed, we want to use the maximum angle. So minimum V naught at the maximum sine of the angle. Sine of 2 theta, well, that's a 45-degree angle. Sine of 2 theta becomes sine of 90 degrees, which just goes to 1. So we're left with r equals v naught squared over g, but we're going to solve that for v naught, and it's square root of rg. Plug in the range, 15 times 10 to the third meters times g, and we get 383.4 meters per second. And then to find the time, well, let's relate to the horizontal distance. X equals v naught x times t, which means that time in flight is the horizontal distance divided by v naught x. Now, we already know the horizontal distance. We were told that that's 15,000 meters. And then we're going to divide by v naught cosine theta naught, because that's the x component of velocity. So v naught and cosine 45 degrees, we found v naught in the first question, 383.4 meters per second. So we plug all those values in, we get 55.3 seconds. Number 85 says charged particles, so we're looking at electrically charged particles, round a 1.2 kilometer radius circular particle accelerator at nearly the speed of light. Find the period and the centripetal acceleration of the charged particles. All right, so we're talking about circular motion. We have a radius of 1,200 meters, nearly the speed of light. We'll just use the speed of light. It's just a little short of this. So v equals 3 times 10 to the 8th meters per second. I've written that with one significant figure, but really it could be three significant figures, 3.00 times 10 to the 8th meters per second. To find the period, well, let's think about the relationships between the different quantities. Going around in a circle, speed is distance over time. So going around a circle, that's circumference divided by period. 2 pi r divided by period. Solving for period t, that means t is 2 pi r over v. And we know all those quantities. Let's plug them in. T is 2 pi times 1,200 meters divided by v, which is 3.00 times 10 to the 8th meters per second. And we get a period of 2.5 times 10 to the negative 5 seconds. Very, very fast. Now, part B is asking what is the radial or centripetal acceleration, and that's v squared over r. Well, we know v, we know r, those were given in the information. So 3 times 10 to the 8th meters per second, we're going to square that, divide by 1,200 meters, and we get 7.5 times 10 to the 13th meters per second squared. Number 89, another question involving uniform circular motion. A neutron star has 12-kilometer radius, and rotation period of 1 second. What's the centripetal acceleration on its surface at the equator? So a point on the surface is going around in a circle of radius 12,000 meters. Period is 1 second. Let's use the equation we used in the previous problem that speed is 2 pi r over t. Also, radial acceleration is v squared over r. I'm going to replace v, because we don't know directly what v is, but we're going to replace v with this expression, 2 pi r over t. So the v squared becomes 2 pi r over t squared, and then remember we're still dividing by r, which means that radial acceleration is, when we clean up that expression, 4 pi squared r over t squared. And then we plug in those values, 4 pi squared times 12,000 meters, divide by 1 second squared, and we get a radial acceleration of 4.7 times 10 to the 5th meters per second squared. That is the end of the Chapter 3 homework. Have a great day.